Hello students, and welcome to another HSC chemistry video tutorial. This one's going to look at alcohols, carboxylic acids and esters. And we're going to have a look at how when we combine two of these groups together we can form the third in a process known as esterification. First I'm going to look at the alcohols. Now the alcohols belong to a very important homologous series. Remember, homologous series are series where there is a similarity in the functional group. And this homologous series are called the alkanols, and they're characterized by this particular functional group here, the OH group. We have some familiarity with these before. For example, ethanol. If I just draw ethanol here, forgive the bonds. Okay, so hydrogens, hydrogens, hydrogens all the way around here, and of course an OH group here. Okay, so this is ethanol, 2 carbons is an F, and the enol bit is a result of the OH group. Now we're going to concentrate on primary alcohols. Now primary alcohols is where the OH group is attached to an end carbon. Now the OH group doesn't have to be attached to an end carbon, it does for ethanol, but it doesn't necessarily for something like propanol. So again, we've learned that where there is no ambiguity, you don't need to use a numbering system. But the problem with propanol, if I just write propanol, is it's got 3 carbons. So I can have it on an end carbon, or I could have it on a central carbon. So therefore, propanol is not a good name because it doesn't really tell me enough. What I want, if I'm going to concentrate on a primary alcohol, is I want propan 1-ol, and then I know that this is not an oxygen, it's a hydrogen, and my OH group is on the end carbon. And you can finish filling these in. So if we're going to look at our alcohols, then we're looking at methanol for 1, ethanol for 2 carbons, propanol, which will be propan 1-ol for 3 carbons, butane 1-ol for 4 carbons, and so on. The other important group that we're looking at today is the carboxylic acids. Now the carboxylic acids also belong to a homologous series, and they are called, their IUPAC name is the alkanoic acids. They're characterized by this COOH group. Okay, and we've looked at, again, most common example is the ethanoic acid, the component acid in vinegar. F because there's 2, so this is ethanoic acid. Okay, sometimes referred to as acetic acid. Now another one that's very important, or that you will run across, is methanoic acid. Okay, or formic acid. What would that look like? Well, it's only got 1 carbon, so OH, 1, 2, and just an H there. Okay, 4 bonds, always important around that central carbon. And because it's only 1 carbon for a meth group, that's ethanoic acid or formic acid. That's what you smell if you crush an ant. Now, these being acids, they will fall into our Bronsted-Lowry definition, and therefore they can lose an OH, a hydrogen, a proton. There we are. There's the proton that disappears. Now, if that disappears, and what we end up with is COO minus group. So if we lose an H+, we're going to go down by a hydrogen, but we're also going to go down by a charge. And because this is neutral, this has to have a charge of -1. That makes a nice salt, okay, a salt. And we know that these organic acids, generally speaking, tend to be weak acids, which means their salts will be strongly basic, or at least more basic than the acids are in an equivalence from neutrality. So what we're going to do then is we're going to form a salt. When we add an alcohol and an acid together, we're going to form a salt, an alkanoate salt. So for example, from methanoic acid, we would have a methanoate. From ethanoic acid, we would have an ethanoate. So what happens when we put these two together? When we put them together, we get an ester. The important thing about esters is that we produce an ester by reacting an alcohol with a carboxylic acid. Now, generally speaking, for reasons that will become clear in the next video, this does not happen spontaneously. We need to help it along. One of the best ways to increase the rate of reaction is to use a catalyst. In this case, the catalyst is H2SO4, which I hope you'll recognize as sulfuric acid. This is concentrated sulfuric acid, and the concentrated sulfuric acid is a dehydrating agent, and it will actually pull water out of this reaction. So let's have a look at it. Here's an example of an esterification process. Ethanoic acid, there's our acid, reacting with methanol, that's our alcohol, forms methyl ethanoate. I'll explain that name in just a moment. That's our ester. And the other product is water. The H2SO4 concentrated version is a catalyst. So you often find it written above the arrow. And of course, this is an equilibrium arrow, suggesting that this is an equilibrium reaction and it won't actually proceed to completion. And again, that's going to be important in the next video. The naming of an ester comes from the first part of the name comes from the alcohol. So methanol becomes methyl, and the acid is the second part of the name. So that's the anion part of the salt, and that comes from the acid. So if it's ethanoic acid, it must be ethanoate. It's going to take a little bit of practice to try and get used to naming each of these, but we'll give you plenty of examples to practice on. And here's one. In 2012, there was a question on the HSC paper, question 21A, or question 21 was actually focused on esters, but A in particular asked you to write a balanced chemical equation using structural formulae for the formation of ethyl butanoate. So, ethyl butanoate. So this name is coming from the acid, and this name is coming from the alcohol. Because it's an ethyl, it must be coming from ethanol. And because butanoate, it must be coming from butanoic or butyric acid. When these form, in fact, we wouldn't have one of those arrows, we'd have one of these arrows. We would form, one product is ethyl butanoate, we already know that, because we were told that's what we have to form, and water. So there's our equation, but it's not balanced. Well, it kind of is, but it's certainly not structural. So let's see if we can draw these structures. So ethanol is 2. There's no H group here. For simplicity's sake, and because I don't want the video to run on too long, I'm going to assume that all of these others here are hydrogens. I'm going to add butanoic acid, 2, 3, 4, and off the end carbon is the OOH. 1, 2, 3, 4, 5, 6, 7. All of those will be hydrogens as well. Now, when these react, we're going to find that we're going to get a water. Now, for reasons that will become clear later on, I'm just going to circle the OH and the H here, but I'm going to underline the OH here and the H here. Okay, it doesn't actually matter which one you choose, the same result in compound occurs. But the H and the OH are going to produce the water, H2O. And then the other product, which I'll draw just below that, is our ester. I'm going to start here, so I've got 1, 2, okay? And then when I come further across, I'm going to lose the OH here, but I'm going to have an O here. And if that's where that's being lost from, that's where the bond is. So there's an O, which goes to a C, and a double bond O, so that's here. And then there are 3 more. 1, 2, 3. And then we just fill up with hydrogens, as we've done in the past. Okay, 2 bonds for each oxygen and 4 for each carbon, and then all of these will be hydrogens. Okay, you can add them in later on. Notice that when you're looking at esters, the key part of the ester to look at is this section here. So this section here is the remnant, and this tells you where the acid was. An alcohol does not have a double bonded oxygen, so if you see the double bonded oxygen, that must be a carbon that's attached to the original acid molecule when this was formed. Because you're taking one OH and an H out of here, they're going to form the water molecule, and then everything that's left, provided you make sure that you transfer it across into your ester, is going to make sure that your equation is balanced. Thanks for listening.